Hello everyone, today I will be sharing my insights on analyzing the structure of parallel programs using MPI style intermediate representations and quaternion graphs. We have already implemented the image processing tasks like the contrast stretching in both OpenMP and MPI in this course. The code itself is not complex, but it's difficult to directly understand what it's doing from a purely C++ course source code perspective. So what does the parallel phase actually look like? How does the data flow between different spreads operate? And when do we do the synchronization and communication? Therefore, in this project, I try to borrow ideas from MLIR and abstract the program back into a higher level IR, which each operation is an independent operation, such as mp.parallel for or mpi.send receive. Then these OPs are converted into a computer graph, which clearly shows which parts can be parallelized, which nodes are synchronization or communication but next, and what are the fundamental differences in the computational structures of OpenMP and MPI. In this project, I will use two simple examples, namely the OpenMP and MPI contrast stretching program we have already done in the course to demonstrate the analyze method. So before showing the OpenMP and MPI examples, I want to briefly introduce the two main tools I used during this project, the computation graphs and MLIR style IR. So a computation graph or a DAG is simply a graph where each node represents an operation and edges represents dependencies. If two nodes are not connected, then they can run in a parallel, and if one node depends on another, we draw an arrow between them. This makes the parallel structure of a program visible at a glance. For example, we have a reduction followed by a pixel-wise transform, the reduction node from a tree, and the transformer nodes for a large set of independent nodes. To describe these operations clearly, I use IR style intermediate representation. Instead of showing the C++ code or runtime code, I rewrite the program into a small set of higher operations such as omp.parallel4, omp.barrier, mpi.lreduce, or mpi.sendReceive. The AIR also uses SSA variables like so every piece of data it has a single explicit definition. So the reason for introducing this IR is that I think it makes the program data flow communication points and synchronization points extremely explicit. And once everything is written as a sequence of higher level opers, it becomes straightforward to convert the IR into a computational graph. So the goal is not to build a truly runnable compiler, but I want to use a simplified MLIR-like notation to review the parallel execution structure of our MPI and MPI stretching programs, and to highlight where parallelism is available and where it is limited by communication or synchronization. So now I will use the contrast stretching node we drew on OpenMP as the first case study. The full C++ implementation as a loop over the number of steps, and inside each step you use a program OpenMP parallel for over the image rows with a nested loop over the kernel. Each thread repeatedly calls the stretch 1 pixel to update 1 pixel in the temporary image, and after that the program copies it back to the original image. And in my MLIR style IR, I calculate the structure with just two high-level operations per step. First, there is a omp.parallel4 operation that represents the entire parallel processing of interior pixels. And second, there is a CS or contrast stretching copyback operation that performs the sequential copy from the temporary image into the back image. So on the side, you can see a simplified error that looks like this. We allocate a temporary image, then for each step we run OpenMP parallel for over the rows and columns, and then finally we call the cs.copyback. The details of stretching 1 pixel are treated as backblocks. What matters is that this work is independent for each pixel and fits naturally into the parallel form. So once we have this IR, it's very simple to turn into a computational graph. So for each step, I group the picture computations by row and it represents each row as a node labeled P or row 1 or row 2 and so on. And all of these nodes are independent of each other, so they appear side by side in the graph, and they can potentially execute in parallel. So after the all row nodes finish, there's a single copy back node that depends on every row. This node represents the sequential phase that copies the resource back into the original image memory location address. So if we stack after row step in the time, the graph becomes a sequence of layers, a layer of parallel row nodes followed by a copy back node step 1, and then the next step starts with a parallel row nodes and another copy back node for the copy back part. So this graph makes the structure of the OpenMP program very clear, I think. You can see almost all the work inside each step is a parallel across rows, but each step has a small sequential region that performs the crucial parts, the copy back operation that must run after all threads finish up this. And so this is for the OpenMP part. So now I will look at the MPI version of the contract program as we done in the project 3. So in the actual implementation, rank 0 reads the input image and then use MPI to broadcast the image dimensions and number steps and shapes and to all other ranks of workers. And next, it scatters continuous blocks of row to each process, and every process allocates a small blocks with 2 extra hello rows, or we call it ghost rows, one at the top and one at the bottom. To simplify this in my MLIR style IR, I introduce a set of higher level MPI operations, and the MPI broadcast distributes the metadata, and MPI scatter splits the image into local chunks, and cs.add hello rows. It turns the chunk into a local block with hellos or the ghost lines. So inside the main loop over steps, each iteration consists of 4 logical phases. The first is the exchange part, the modeled as a single MPI send receive operation. This represents the MPI send receive calls between neighbors ranks that exchange the ghost rows and the top and the bottom boundary rows. The different ranks play different roles. For example, the main process exchange only with rank 1 mid workers exchange with both neighbors, and they are basically the abstract into the same operation for the IR because we want to make it simple and explicit. The second part is the local computation phase, which is represented by the cs.local contrast step. So here each rank or loops over its interior rows and columns and calls stretch 1 pixel function on each pixel inside its block, and the accumulates a local difference counter. And then we have a global reduction represented by the MPI.reduce_add, which combines all the local different values into a single difference total on the rank 0 worker. So, and then we finally have a copy back phase. The cs.copyback blocks with each rank copies their updated from pixels from the temporary block back into its local image block. After all steps finish, a simple MPI gather image operation collects the local blocks back to the rank 0 to form the final contrast stretched image, which is then written back to like the final output or the disk. So when we convert this IR into a computational graph, each rank appears as a individual loop, and in the every step, each rank has a hello exchange node, which is followed by a local contrast stretching, and then we have a MPI reduce, and then we have a copy back node. So the hello exchange nodes are the connected across neighbor ranks, and in the graph we just make it connect to the all of the ranks to make the graph simple. And because the MPI send receive couples their boundary rows, all local compute nodes must wait the send receive to finish. All the local compute nodes in the same step fit into a single reduce node that represents the MPI reduce add on the difference. This graphically shows that there is plenty of parallelism in the local computation phase, but it also have a lot of plenty of plenty of the combination points that lenses the critical paths. And compared to the OpenMP graph, we can see the additional explicit communication rows that ties the ranks along together and limit how far the computation can be overlapped. So this is the two IR graphs that or computation graph I've made in this project. So to conclude, the main goal of this project was not to optimize OpenMP or MPI implementations themselves, but helps us to better understand the apparel structure more clearly by rewriting both versions of the contrast stretching program in MLIR style intermediate representation. Each major step per loops, hello exchange, reductions, and copy back phases becomes an explicit high-level operation. This makes the program much easier to reason about rather than using the original C++ code files with programs and MPI calls. Once expressed in this IR, we can directly translate the program into computation graphs, which visually expose the available parallelism and just as importantly, the points where the synchronization and communication occur. In the OpenMP case, the graph shows most independent per row work with a small sequence bottleneck. In the contrast, the MPI graph highlights multiple layers of communication, hello exchange between neighbors, and global reductions that extended the critical path. Overall, this MLIR-inspired approach provides a clean and more interesting way to examine and compare different parallel programming models, and it helps me to review with two programs as they implemented the same algorithm may exhibit a very different scaling behavior simply because the execution graph have different structures. So that's all of my project. Thank you for your listening.